In this video, we're going to talk about Green's theorem. Or at least, we're going to talk about part one of Green's theorem, the part that talks about curl or circulation, or sometimes it's called the tangential form of Green's theorem. So here's the idea. Imagine I have a vector field, and I have some curve that goes around the vector field. As I saw in the previous video where we introduced the notion of the circulation density or the curl at a particular point, we've seen that at any specific point, I can measure the degree to which my field is causing a little propeller to spin at that particular point. There's one spot, and then we can look at a few others here, and in fact, we can put one right on the boundary if we so did. So depending on what the field is, you go in and measure at some spot and put a little propeller there. It might rotate clockwise or counterclockwise, faster or slower. It just depends on what the underlying field is. This notion of spinning at a specific point, we previously called the circulation density, and we'd seen how to come up with a formula for it, which was the partial of n with respect to x minus the partial of m with respect to y. And that measure gave a degree to which you'd have spinning at a particular point. So that's a local property. But we've also seen what I'll call a global property, which is the circulation around the blue curve. Now, the magic of Green's theorem is that these two different concepts, one a global property along a full curve, the other a local property at every specific point, can be related, can be stated in the same formula. So let's check it out. Let me take a generic curve, and I'm going to think about the curve and just ignore the underlying field for a moment here. And I've also shaded in a region that is enclosed by the curve. A little bit later on, we're going to have some conditions on this curve. It, for example, needs to be a closed curve. That means it comes back together. And it also has to be what we call a simple curve, which means it has no self-intersections. The point of these conditions are to talk about curves that enclose a specific region. Now, I could compute the circulation along this curve if I wished. But let me do something else. Let me cut this region. So I'm going to come here, and I'm just going to cut it up and divide it now into two different regions. There's a C1 curve that wraps around the first region on the left, and a C2 curve that wraps around the second region on the right. And then note carefully that to keep the complete counterclockwise rotation of the curve, that what happens when you go along the cut is on the C1 you're going up along the cut, and along the C2 you're going down along the cut. They're in opposite directions. Now notice the next point, which is that if I compute the line integral along the broader curve, it's just the sum of the line integral along the C1 and the sum of the integral along the C2. The line integral is just written as this sum. And the reason this works is because along that middle portion here, well, everything just cancels. The same line, it's just they're in opposite directions. So along one of the integrals, if it turned out to be, say, positive, along the other integral, it would be negative because of the opposite direction. So the point is, I can cut my region, create these two curves, which, yes, they are longer in total length, but the extra length that's created along the cut, that just cancels out. And in fact, I could just do this over and over and over again. Well, what if I just took my region and cut it in more smaller and smaller pieces and had n little subregions? Well, the same story would be true. I could say my total line integral around just the outside was the sum of all the little line integrals around all the little regions that had been resulting from all of my cutting. Basically, everywhere in the middle, you just get internal cancellation. You have the line integral in one direction and then the corresponding line integral right back in the opposite direction with a negative sign being introduced. So all that's left when you add up line integrals around all these little rectangles is, nevertheless, just the final boundary, the line integral just along the boundary. Okay, now here's where the real magic comes in. If I focus on just one specific little region here, so I'm imagining a tiny little rectangle, and I'm computing, well, what is the circulation around that line integral? What is the line integral going to be? Well, in our previous video, when we introduced the notion of circulation density, we computed that the line integral around some infinitesimal rectangle could just be given by the circulation density, partial of n with respect to x, minus the partial of n with respect to y, times the area delta x delta y. And so now I'm starting to get this relationship between the total circulation around the entire curve and then the circulation density around these tiny sort of infinitesimal rectangles when I cut it up more and more and more. So if I take the limit as n goes to infinity, what I get is called Green's theorem. And it says that the line integral around a curve is, you just take that circulation density and you add it up, and a whole bunch of accumulations. This is just a double integral. So in other words, the line integral around the curve, the f dot dr, is the double integral over the enclosed region of the circulation density and then integrate with respect to the little area, this dA or dx dy if you prefer. So basically what I'm saying here is that on the left I have my counterclockwise circulation as I go around this curve. And then on the right-hand side, I am integrating the circulation density. So Green's theorem in its circulation curl form is just saying the total circulation is just integrating up over all of the area, the circulation density. I have some regularity conditions on my curve and on my field. They have to be relatively nice. The most important of those conditions is specifically that it's a simple closed curve, and that was going to imply that we had a single region R that could be described from our particular curve, and the region was enclosed by that curve. Okay, so to help visualize this again, if I have my region enclosed by my curve and I'm trying to take the circulation around the boundary of that region, then I can imagine at any point here, I can have a whole bunch of different little spinners where I come down and measure the circulation density. I just put 4, but it would go all the way around the boundary and indeed all the way in the middle. And then at each point along the boundary, this tendency to spin at that particular point is going to contribute to that portion of the circulation along the boundary. Now, this should seem very strange, because circulation is something that only occurs around the boundary. It doesn't matter what's going on the inside, right? Circulation is just a measure along a boundary. But we're saying that is equal to a double integral, an area integral. An area integral with all of our circulation densities where it really does matter what's going along in the middle. It would matter what these spinners are doing in the inside. But if you think back to what the fundamental theorem of calculus does, it actually has some similar behaviors. When you integrate some derivative and get that the answer is f of b minus f of a minus f of a represent just what happens on the boundary of some interval. And somehow the difference of the boundary of some interval is related to integrating over the entire interval. And so similarly here, we're relating information over the entire region, the information of the circulation density, and accumulating it all up. And that results in just the circulation along the boundary. All right, in the next video, we're actually going to compute a line integral via Green's theorem and see how to do that in a concrete example. So if you have any questions about this video, please leave them down in the comments below. If you would like the video for the YouTube algorithm, that would be much appreciated. And we'll do some more math in the next video.